many results here. I think we won't have time for all of this, but here's the like rough content. Like intuitively, the paper is about fairness and efficiency of allocating resources among network agents. And I'll tell you later what all these concepts mean. So I'm just reading to you now. And so I'll first review the literature. Then I will define. I will define like a family of graphs which are interesting within the paper, and I will give you some simple graph theoretic results about these graphs, which are not our own, but on which our result relies. Then I will tell you our main result about the trade-off of fairness and efficiency, then I will tell you how this result pertains to some classic fair division concepts and also to our own fair division concept. So, okay, what I want you to keep in mind is that there will be first some results about graph theory, but they are not the most important. They are not our own. They are just essential results.
Everybody here likes graph theory, right?
Yeah. Nice. So here's the setting. So consider something like. Consider something like poverty or disaster relief, where the government allocates money to people, and people care about each other. So, for example, if Gilad is my friend, I don't only want to receive money myself, but I'm also happy when Gilad gets some money. So these altruistic externalities, they are captured by a graph. So the graphs we'll consider are not directed and not weighted, but not necessarily connected. So they can be separate connected components. So in the basic setting, this is the utility function. So V is called the social utility function. V is called the social utility function. It consists of the allocation vector x. So the allocation vector x specifies who of these finite set of agents gets so much. And for agent indexed I, it depends on her so-called discount factor, delta I. So how does it work? If the allocation is x, I get my allocation xi plus this sum, so it's a weighted sum of others' allocations, and I weight, if I'm agent I discount the allocation to agent j with my discount factor delta I to the power of the graph.
So this is what NV3?
To the power of the network distance from me to agent j.
This is NV3. So if Gilad gets money, I'm happy, but at a certain point he gets more than me, and then it's not that fun.
Yes, there are no envy concerns, but we will study how like the classic fairness concepts, including something like envy-freeness fairs in this setting. Okay, so it's simple. If, for example, I'm connected to Gilad, if I get $1, I get 1. If he gets $1, I get delta I, where delta I is my discount factor. Like, for the sake of example, let's suppose Yuval is not my direct friend, but he's Gilad's friend. Gilad is my friend. If Yuval gets $1, I get delta I squared.
Okay. I mean, if you take something from me and move it to Gilad, in your setting, okay, less utility. It's not that they really suffer.
I'm not sure what the question is.
So in a sense, the influence of me is not because. So put it this way: suppose that you keep my payment fixed and you increase Gilad.
Yes.
It means that Gilad's ranking in this system becomes higher. It doesn't harm you.
Well, there is no ranking in this system.
No, but why is that surprising? Is it
surprising?
Why?
Yeah, it's very surprising. For
is
example, you're telling me that okay, you will get a certain amount of money from a grant, but now Gilad gets 10 times more than me, and Gilad is more central in the system. You're talking about the network, so there is a measure of centrality here.
But this is not a story here. Why do
That's
you?
what I'm
They are nice people.
This is not
They
a
are
stop.
not envy.
Okay, like again, if your concern is that we don't capture fairness through utilities in this in this setting, then I think you'll be interested in our section when we study fairness concepts in this setting.
You think this is the standard? That there is envy? There is an envy?
Could be many steps.
Okay,
So I'm supposed to think about this as cardinal utility?
yes,
Okay.
And I should think about the connection as being friend,
yes.
and someone with more friends get more money
Should make you happier.
So we do not
because it makes many people happy.
well, not necessarily, but like we may be able to construct a Pareto improvement if we indeed give more money to someone who has more friends and is in some sense more central, in which sense I will explain. No, we don't study like the optimal allocation of resources here that maximizes this utilitarian utility. So it's difficult. Okay, so let me quickly gloss over the literature. Like someone already came up with a similar setting, but for just two agents in the 60s. So they showed that there can be a Pareto improvement if we give money from one person to another when there is altruism. Surprise, surprise.
No, I don't understand. Pareto improvement.
Pareto improvement means that someone is strictly, everyone is weekly better off.
No,
and someone is
I know that. But there's only the two of us, and you give me money because you care about my welfare.
Yeah.
How is that a Pareto improvement?
Well, if we think about utilities as the social utilities I showed you on the previous screen, which include altruism, then if, for example, you are very poor, I'm very rich, and I really care about you, if I give you money, you are happier because you are now richer, I'm happier because I donate money.
I see. So I didn't see what V is. So if my V... No. Where does it say how poor or rich I am?
Yeah, here it's nowhere, but it's a nice example from real life which
Sure,
illustrates the
right.
concept, and there will be concave utility, there will be a case of concave utilities further in the talk as well.
So
where these concerns will matter.
at the moment I can think this is just money.
Yes.
Good.
Alright, like another important paper is Burles et al. 2017 Econometrica. And there they have concave utilities, which we will also study in one of the sections. And there they study a Nash equilibrium when people simultaneously decide how much money to send to each other. So in one of the sections, we'll take their setting and we will look at the existence of allocations which are Pareto efficient and or in some sense fair, in some sense robustly, and I will explain in which sense. Okay, I keep feeding you promises. Right, and there is like this old Games Economic Behavior paper where they study how unequal can a stable allocation be, and in their sense, stable means that no coalition which forms a complete subgraph can deviate, and their main finding is that if you have many agents who don't have connections to each other, then this society can support more unequal allocation of resources without someone deviating. So we do something different, we have different notions of stability, but if you're interested about this stuff, you can check out the paper. Okay, so let me again give you these graph theoretic notions first, which will be essential for our results, but we don't claim that we discovered them. So like what you see here is called a claw, like it's a star with three periphery agents, like 3 is important, it's exactly 3. And here what you see is a claw, so it's a triangle and a leaf attached.
What's the difference?
Because here there is a triangle, here there is no triangle.
And one of them looks like a claw and the other like a claw. Okay.
Claw and sport, so they, not examples, they exactly like this. So like exactly 4 agents. For claw there are 3, one's in the periphery, one center. For core, there is one triangle and there is one leaf attached to the triangle. So we define inclusive networks if it does not, as a network which does not contain a claw or a core as an induced subgraph. So, and I will give you some equivalent definitions later on, but like if you don't know, so let me also comment what's induced subgraph. So here, like the blue graph is an induced subgraph of the whole graph. So we borrow the vertices, we borrow the edges between them, and if there is no edge in the subgraph, we cannot draw it in the big graph. So for example, if there is no edge like here, edge here in the blue graph, we cannot, it should not be there in the blue graph which contains, it can't be in the black graph which contains the blue graph as an induced subgraph.
So this includes point.
Sorry?
This includes.
This is claw.
What is this?
The blue one is a claw?
The blue one is
the
a
blue.
claw.
I didn't see the difference between the colors.
I'm sorry.
And above it, it's a claw. Yeah?
So this is a claw and it's an induced subgraph.
And the paw, it's above. Okay.
And this is a paw, by the way, yes.
Okay.
And this is a paw. So, but for example, this one we don't consider it as a paw as an induced subgraph. Actually, we do. Yes. Okay, fine. Like I hope you. I just wanted to show what an induced subgraph is.
So what is it? I take a subset of vertices.
A subset of vertices.
And I take all the edges between these vertices,
you take all the vertices between all the edges between these vertices, and you don't draw any new edges.
Sure. Okay.
That's it. That's a new subgraph. Okay. So equivalently, like a network is inclusive if and only if each.
So just to be sure, if I draw here, if in the original network was here an edge and here an edge, this wasn't a paw anymore. Because I couldn't just draw the edge, right?
Yes, you cannot draw the edge. So for example, you cannot. So you want to make this not a paw, right?
Yeah. So you take it exactly.
Then this one you cannot draw. Okay.
No. I say, if originally there was an edge here.
Here. If originally there was an edge here, then this is not an induced paw. Yes, exactly. Yeah. So equivalently, an inclusive network is a network where each component is a cycle, chain, complete graph, or a graph which we call almost complete, in the sense that in every component you can have at most one non-friend in this component. So, for example, if we are
slowly, I didn't get that. This is the definition. That is a new definition, by the way.
It's an equivalent definition.
The first one, the concept is a new one.
Yes.
Okay. So the equivalent definition says.
The equivalent definition says that a network is inclusive if and only if every connected component. Let me show you on the same slide. It's a chain, a cycle, a complete graph, or it's like almost complete graph. So you can think of this as complete minus matching.
Minus match.
What is matching?
Minus you can take two people, delete an edge between them, and then don't delete edges between these people anymore.
But how many edges can I delete?
For each person, you can delete just one edge from a complete graph.
For each person?
Yes.
So I can delete many couples, but each person is only deleted once.
Each
Each
edge coming out of the person can be deleted at most once.
If you have 1, 2, you can only eliminate 1, 2, but then you cannot eliminate 1, 3, for example.
Okay.
I didn't understand the general definition.
Unfriending, you can unfriend one person.
No, yes, this I understood, but inclusive. What?
Okay, this one you understand. It does not contain
It does not contain a claw or paw. Okay, this I understood.
So this is an equivalent definition. Like it's not obviously equivalent, but they are.
Okay.
And the equivalent definition is that every connected component such a graph must be must be chain cycle complete. All these almost complete we're discussing.
Okay.
So again, the way I think about almost complete, suppose we are all in a kinetic component, and suppose that for every one of us, everyone else in the room is a friend except possibly one person. I don't know. For example, for the sake of example, I don't mean it. Suppose I'm friends with everyone. It's okay. Suppose like Yoav is also friends of everyone, but maybe he's not a friend of Gilad, but for everyone else he's a friend. So it's only for the sake of example, and so on. So each of us is either a friend of everyone else in the room, or he's a friend of everyone else in the room but one person. And every component. So if so it's one of the allowed components.
So is this a new definition or an existing one?
It's an existing one.
But it was written there. There were a couple of that were cited.
Yes.
So this is the only adopted here that's existing, and people in the literature are very familiar with it. It's only new to us.
Okay, it's not familiar in economics, so so we are introducing the term inclusive networks.
Where it appeared mostly in which type of literature?
Like the term inclusive networks appears first time in our paper. Like the object itself, is known as Claw and Porphyry graphs in graph theory. So it appeared. I think like the most major appearance is this paper. It's I think open journal of discrete applied mathematics, something like this. And it's like a relatively simple result where they say that okay, this is equivalent to this. Okay. So it's known, but it's very rarely used in fact.
This is something that will be a key to one of your main.
Yes.
But what you said now, it sounds like you can alternatively define it as a graph. Each vertex has most
Yes.
has minimum.
Okay.
So it's just okay. I understand. Just one way, one group of inclusive graphs.
One group of networks. So like if
They are inclusive graphs with other definition. Okay.
okay. And like the last equivalent definition that in every component, so it goes with what you say, in every component either you have two or less friends, so it includes a path or cycle, or you have
More than n.
or you have more than n, like
Either this or this.
weekly, or you have weekly more
So
than
you
n.
have at most two these friends.
Sorry?
People are not your friends.
Yeah, have either like just two of your friends, or no. Here you have one non-friend. Yeah, one. So these are three equivalent definitions. I think the most intuitive is like this one.
The last one is
this is inclusive. This is not inclusive because it's a core. This is not inclusive because it's a claw. Alright. So another definition that's a new definition that's ours. So we call a network uniformly efficient if every interior allocation is Pareto efficient. So by interior we mean that for every person her allocation xi is strictly positive.
The allocation is
Strictly positive.
interior, so nobody gets zero.
Nobody gets zero, yes.
And can some? Okay.
So nobody agrees to someone they know getting a zero, including them, of course.
Well, we did not, so either me or you.
You may see infinity. It's like the last person I know, he cannot receive a zero.
The allocation is that no one receives zero, but there is no agreement thing. We have not defined any agreement thing. So, interior is just like a thing about vectors. It's a strictly positive allocation vector where the allocations sum up to one. Uniformly efficient, it means that some allocation where everyone gets strictly more than zero is Pareto optimal for all discount factors. So it means that we can fix this endowments, we can play around with discount factors, and it will always stay Pareto efficient.
For any possible discount factors,
Yes.
profile of discount factors.
Yes.
Including also 0 and 1.
No, 0 and 1.
Strictly
No, 0 and 1 are not included. So discount factors between 0 and 1 still here. Yeah, and it's also equivalent to, it's equivalent to the following thing, that any interior allocation is Pareto efficient. So in this setting with linear payoffs, we can call the network uniformly efficient if only some allocation is always Pareto efficient, or if all interior allocations are always Pareto efficient. It turns out it will be the same by the linearity.
Any what? Any?
Yes, okay.
Any interior allocation.
Yes.
Right?
Yes, so we can, these are going to be two equivalent properties. One property is that any interior allocation is always Pareto efficient.
What is an interior allocation?
Every agent gets a strictly positive allocation.
Nobody gets zero.
Nobody gets zero.
Any interior allocation is uniformly efficient? Or is it?
Okay, like definition.
Okay,
No. Any
This one is
interior allocation. Two definitions. One, some interior allocation is Pareto efficient, right? The other, any interior allocation is Pareto efficient.
and they are equivalent.
And they are equivalent.
So you can change some to any and then.
Yes. Yes. Okay, can I go on?
No, theorem.
Yeah.
You almost forgot.
Yes,
Thank you.
Thanks, I'm surprised it's on the same slide. Okay, so a network is uniformly efficient, so it has this property, even only if it is inclusive. Like that's our first result. So for example, this network on the board, it's not inclusive because it contains a claw, for example, and also it contains a pore, like this. And so it's not uniformly efficient. So it turns out that if we have any allocation where everyone gets a positive amount of dollars, for some discount factors which model
For
the
any
algorithm-
discount factor?
No, for some. Okay. Let's start the definition. So, like in this network, if everyone gets a strictly positive amount of dollars, like we can find such discount factors which model altruism, that there will be a Pareto improvement. Okay.
So simply, if you take a claw,
Yes.
it already isn't uniformly efficient, right?
Yes.
And can you tell me why, or is it complicated?
I can give you an intuition. Okay, I can give you like a very simple proof sketch. Okay, so let's consider first the claw. Okay. So let's first forget about these guys, just the claw. So in the claw, suppose that here's delta 1, delta 2, delta 3, delta 4, and suppose that delta 1 is almost 1, delta 2 is almost 1, delta 3 is almost 1, so that they're not exactly 1, but they're very sufficiently close to 1, okay? So in that case, it's not surprising that we can send a little bit of money from this guy to the central guy, a little bit of money from this guy to the central guy, a little bit of money from this guy to the central guy. And because their delta is so large, they're all better off. So because I'm losing a little bit, but I'm getting because.
So why not to give everything to the central guy?
It's also possible, but we need to ensure that everyone sends the same amount to make sure the improvement is an improvement. And we also want to make sure they have enough funds to send. So if they send the same small epsilon, this works for sure. But
No, I didn't understand.
okay,
Why it's not Pareto efficient to give everything to the center?
it is Pareto efficient.
So what's the problem? We say that only.
Well, I was.
It's not uniformly efficient.
Yes, so I did not want to
Not
say.
for all the.
So I said, I did not say which
Interior
allocations.
allocation. Okay.
Which allocations are Pareto efficient? Yes, so what I want to show that the interior allocations are Pareto efficient, like why? Because we can send a small amount to the center. Okay, one other comment. So it's less obvious with this kind of graph because here it's clear the periphery guys benefit. Here it's not clear because there are these other guys. But again, since we are free to change the discount factors which model altruism, we can say, okay, let's suppose this guy very altruistic. So let's suppose these blue guys, they're very altruistic, and everybody else is very selfish. Well, in this case, if these guys, in this case, we do a slightly different thing. So we send a small amount from here to here, here to here, here to here, but we also send a small amount to all these guys to compensate them for losing. So, like for some discount factors, we can decrease the amounts that we send to the central guy here and to the guys outside of this claw to make sure it's a Pareto improvement. That's right. Okay, now you can ask me why do I care about interior allocations because there is altruism. Well, then it turns out that it pertains to some, it turns out that we can use this result for more general settings. So you can think of this result as more technical. Okay, so first of all, let's assume we have concave utilities. So it's the same thing we saw before, but we're replacing.
With the linear series, would you give us some sketch of proof?
It was it.
So one of the sides is clear why this chloroform makes problem.
Okay.
But the other side is the one that I'm interested in.
Okay. The other side is more complicated, but usually it's by induction. So for the complete graph, I think it's pretty simple. For the complete graph, if for the complete graph, someone
This is
was
not complete.
okay. Thanks. Okay, for the complete graph, I think it's clear. Someone must be a net loser. Okay, if we reallocate the amounts of money, someone must be a net loser, so someone must lose money because the total allocation is fixed to 1.
Even if the delta are different?
Sorry?
If the delta are the same, it's clear by symmetry, but if the delta are
Even if the delta is different, we send some money to each other, someone must lose money. So he loses money, and all the other people gain, but he discounts the gains of these people by his delta 1, for example, and he loses some amount of money which is not discounted. And these amounts of money are the same. So even if you're all my
The
friends,
average is 0. There's another way to see it. The average is 0
Yes.
of change. So if someone gains, for others it's a pain, right?
Yes. So if I'm the guy for whom it's a pain, then I don't. Then the benefits other people get are not enough to compensate because you gain the amount I lose and I discount your gain. So that's basically if epsilon 1 is negative, then delta vi. Delta v1, if this is person 1, is epsilon 1 plus delta 1 sum I from 2 to n, epsilon I, where epsilon is the distribution, is the amount of net gain or loss. Well, that's equal to minus epsilon 1, so that's epsilon 1 minus delta 1. Epsilon 1, if epsilon 1 is negative, then it's negative. Right, the hardest part, everything else is harder, but we can prove by induction. The toughest part is the chain part.
Induction on what?
Sorry, the chain part. So that the chain is inclusive. So for the chain, for any discount factors, any interior allocation is Pareto efficient.
Induction on the number of vertices.
It's
On the length of a chain. And
Well,
then
it's-
how you,
it's on like actually it's on length of the chain and on the number of agents who receive a strictly negative allocation. Like it's two-way induction. It's a bit complicated to like tell the whole story, but that's the toughest proof.
okay.
Yeah. So yeah, one interesting fact about these inclusive networks is in fact any allocation for them is Pareto efficient. So for all discount factors. So if you make some people zero, it will stay Pareto efficient for all discount factors. So the kind of implication is that if you're a policy maker, you want to distribute money in a Pareto efficient way. If you know that the network is inclusive, you can do whatever you want and it will be Pareto efficient.
But why you care about interior division?
I will tell you. Okay.
This is about inequality or something.
Yes. Okay. So. Yeah, you might. I can see that you would surprise. Maybe we can discuss it a little bit later after the talk. I want to show you some like applications of this. Okay, so let's move to the concave world first. Let's suppose that all utilities are concave. So we're replacing this xi with something called private utility, which is concave, like strictly concave, has some other good properties. And is individual for every agent. Right, and so this is related to the econometric paper where they study a similar setting but without a network structure. So they don't assume any network, they assume a general matrix which models how people care about each other, but we assume it's modeled by a network. Right, so here is a theorem. So there exists in this concave world, there exists an allocation which is Pareto efficient for all discount factors if and only if the network is inclusive. Okay, so again, suppose you care about efficiency. You care about efficiency period, not efficiency plus interiority. You care about efficiency period, and you think that people have concave utilities. Then you can be sure that you can implement something which is going to be always Pareto efficient, no matter how altruistic people is, how they care about each other, if and only if the network has this structure. So for example,
Now you are not talking about interior?
no, but it's implied.
Right, like.
It's implied because I don't know. Suppose I think let's say Ron has no money at all, and I have some money. Well, in that case, if I'm even indirectly connected to Ron because of concave, because of concavity, I'm also suffering if he has no money, so we'll send him a little bit.
But the previous result, the previous assumption of linearity is concave, no? Isn't it?
Here it's strictly concave.
Strictly.
Concave.
So you could add interior and the theorem would be true.
Yes.
And could you also change there exists to every interior? No, now you can because of the.
Now I cannot because if Ron has like a little bit but very little money, still I will.
And any Pareto efficient allocation must be interior.
Yes, it's also true. And a proof sketch is a proof sketch of this is that we're going to use our result about linear allocations. So how we're going to use that? Well, first, if we want something which is always Pareto efficient, then we want the marginal benefits to be equal. Because suppose Ron has a smaller marginal utility of money than me. If all of a sudden I become very altruistic, I really care about all my even indirect friends, I will send money to Ron. So if Ron has a lower, if given the allocation.
Because of concavity. Okay.
If given the allocation, Ron has a smaller marginal benefit than me, well, there exists some utility function which will make it not Pareto efficient. Because if I'm very altruistic, I will want to share with Ron, both I and Ron will be happier. If you're all altruistic, you'll also be happier. So if you want something which is always Pareto efficient, well, it must be that all the marginal benefits are the same. And using that, we can use local linear approximation with linear payoffs and apply our result. something like this. Okay, so I think this is like a bit more applicable than our previous result, which used linear payoffs and interior allocations. Okay, is fine, shall I go on? Right, so now I think going back to like Yuval's original question, it's interesting how some classic fairness concepts fare in this setting. And it turns out that even in the linear world, when everyone has linear utilities, we can say something interesting. So let me like introduce or maybe remind you about some classic fairness definitions, and I'm not sure if it's what Yuval was interested in. But maybe it's a bit similar. So like the most simple definition is egalitarian. Everyone gets the same amount of dollars. Okay, the second one is proportional. So everyone gets more than 1 over n. Like why exactly 1 over n? Well, let's imagine an alternative world where everyone becomes a dictator with the same probability 1 over n. Okay, if I'm a dictator and we're in the linear utilities world, I want everything to myself. So I get 1. If Yuval becomes a dictator, he draws everything to himself, he gets 1. Like again, why he does so? Because we have linear utilities now. So if we live under this random dictatorship, then the expected payment is 1 over n. So the allocation is in some sense fair if everyone can guarantee a payoff which is weakly better than the outcome under this random dictatorship. So it's called proportionality.
Why not to take the utility above n? I mean, if I'm a dictator, my utility was u of 1, right?
We are back in the linear case again.
Oh, okay.
We're back in the linear.
Okay. The definitions from now on, or the discussion from now on, is on the linear case.
Yeah, yes, again, we're back to the linear, so this is clearly maximized. If the x's sum up to 1, this is clearly maximized if xi is.
Linear is clear.
Now it is linear. Right, and so here is non-contestable. I think this is the closest to NV3. So non-contestable means that I don't want to swap allocation with someone. So we borrowed it from this fellow's theoretical economics paper of 2016, where he studies fairness with externalities, like we do. So in our linear setting, this boils down to something very simple. Again, if we have linear externalities, if Ron has more than I do, then of course I'd like to switch with Ron, and so that I get more. Like because it's a linear world, I'd like to do so.
So what do you say? Non-contestable means equally, exactly equal?
Yes.
Okay.
Yes. So in our setting, it's trivial because if it's not equal dollar allocation, it's contestable because I want Ron's wealth if I think he's richer. But we adopted from a more general framework that studies fairness with externalities. Right, and so the proposition is that if we have linear utilities, then we can have an allocation which is Pareto efficient for all discount factors, and which also has any of these properties, if and only if the network is efficient. Is inclusive, sorry, inclusive. If you know the first theorem, it's hardly surprising. Like why? Because to ensure all these concepts, we must give the same amount of dollars to everyone, and it's clearly interior. So if we give 1 over n to everyone, everyone gets more than 0. And so if the network is not inclusive, we can find these discount factors which model altruism, which can allow us to improve this. So the kind of lesson is that if you want, if your government giving out money, you want something which is fair and efficient, and maybe you don't know enough about how altruistic people are. Well, maybe they can change their mind. Maybe you don't know this. Then you have a problem for these non-inclusive networks like this one. And so, like the post lesson would be that you should either design some mechanism to learn people's altruism, or maybe you should gather some data to learn it. Like otherwise, you will fail. You will fail on the fairness or efficiency side. Okay.
So what does the proposition say? Egalitarian or non-contestable?
Or
Non-contestable.
Or.
No, non-contestable, we said it's trivial here, no?
It's trivial. Like it
So
coincides with the
you can drop it from the proposition. Whenever it's egalitarian, it's non-contestable.
Well, yeah. I mean,
No, but the theorem says that if it's non-contestable, then
it's egalitarian and vice versa. Well, it's,
In this context, it's exactly the same.
in this context, it's exactly the same. Yes.
okay.
I mean, it depends on the audience whether you can drop something for a proposition or not. Like you, I think, are very quick to catch all these various concepts, but you know, referees and readers, of course, vary. So we decided to make it more explicit. Right. So, like one possibility result is that you have linear utilities. We can have something which is it's actually like a more impossibility result rather than possibility. So, like with proportionality, we have the same. So we can have something which is proportional and Pareto efficient for all these count factors, if and only if the network is inclusive. How am I doing in terms of time?
Let me
30 minutes.
30 minutes.
32.
32 minutes. Okay. Well, let's.
It's a lot of time or too few?
It's,
No, he sounds around.
it's a lot of time. Okay.
Let me ask something.
Yes.
Right?
Of course.
No, you want. So the proposition is a conclusion of the previous theorem, or?
Yes, it relies on the previous.
It's included in the previous theorem.
It's a consequence of the previous theorem about the
Not
linear
directly. It's the previous theorem says that. So one side it's clear, right? If it's not inclusive, you cannot find an interior
Yes.
solution. So one
Yeah.
side is clear. The other side, that the egalitarian solution is also Pareto. This is something that we have to prove.
Well,
So
it also follows from this theorem. So
Beautifully efficient.
what this theorem says is that if we have one of the networks. Okay, the theorem says that if we have one of the networks like this, okay, like not the red ones,
Yes.
these are inclusive networks.
Inclusive.
Like for them, every interior allocation is Pareto efficient for all these count factors,
Agree.
which model altruism, and like moreover, every allocation period.
So it's a direct conclusion.
It is a direct conclusion.
Just understand.
It is a direct consequence. Yeah. Okay.
By the way, why is it called inclusive?
Why it's called inclusive? Well, kind of because we can include everyone in the sharing of benefits, and this will not have any bad properties.
Okay, so this is not a direct property of the network. It's a property of using the network for allocation.
Yes.
Okay.
Well, in a sense, but it's just it's just like a name. Like we were just too modest to call it, Samsonov, Fomichev, and Shahir, and Safi networks. All right. So yeah. Anyway, like what we have shown so far is that like for inclusive networks, we should have seen like we can have something fair and efficient at the same time. For everything else, we cannot have the same thing, like robustly for all these count factors. Now, I want to show you one more result in this spirit. So let's assume concave utilities again. So let's assume concave utilities again like this. And so for these ones, like as one can find in this paper, individuals would like to send some money to each other if they, if like to someone who is poor. in the linear world it's not possible, but in the concave world, like I can send money to Ron if I think he's poor, and vice versa. Right, so with this framework, we introduce our own new definition of fairness. We decided to call it charity-free. So charity-free means the following, like basically charity-free allocation is that no one wants to send some amount of money to another person unilaterally. So like equivalently we could say that there is a Nash equilibrium in a non-cooperative game where everyone simultaneously decides how much money to send to another person. And that's what they study in this burlesque paper. But we also think of this as a fairness concept. So for example, if I think the society is unfair, then I don't know, I tip the waiter or I donate some money to a charity that helps poor people. Right, and
So you get to the point where it's charity free because you have already transferred what people want to transfer? Is that what you said?
well, actually, this burlesque paper, it shows that yes, indeed, if you start with some allocation and you allow people to
Transfer money.
you allow people to best respond, then the best response dynamics are going to converge to this charity-free allocation. So because this game,
Potential games.
because this game is a potential game, yes, but we are not focusing on this question. We just care about the existence of an allocation with this property plus something else. So what we show, surprise, is that, like, first of all, if we want an allocation which is like this, which is charity-free for all discount factors, then all the marginal benefits must be the same. So that's hardly surprising because,
Otherwise, we want to.
yes, it's hardly surprising because if someone has a lower marginal benefits, if everyone is very altruistic, then if I send the money to someone who is poor, everyone benefits. So like a necessary condition is that all the marginal benefits are the same if you want something which is charity-free for all discount factors. And like there is an allocation which is charity-free and Pareto efficient for all discount factors if and only if the network is inclusive. So this statement is weaker than our previous theorem about concave utilities. So remember what I told you already, that we can have something which is Pareto efficient for all discount factors, period, if and only if the network is inclusive. And now I'm adding charity-free on top of that. So if the network is like this, it's non-inclusive, there is this claw, then there is no allocation in the concave world, which is Pareto efficient for all discount factors. And so clearly there is no allocation which is Pareto efficient and also charity-free for all discount factors. But on the other hand, on the other side is stronger. For example, if we have a chain, then in the new theorem, we say that, okay, we can have an allocation which is not just Pareto efficient for all discount factors, it's also charity-free for all discount factors. Well, like again, and if you understand all the definitions, it's almost a direct conclusion of the previous theorem plus the observation that if you want something charity-free for all discount factors, the marginal benefits must be constant across all players, at least in the same component. I'm sorry. Well, how am I doing in terms of time?
25.
Like more than enough.
12:30. Well, it's okay to finish early, but
No,
nobody does.
Okay. I have more results. So what I want to show you else is like first of all there are some interesting results about fairness in this setting which do not use our inclusive networks. And second, there are extensions where we choose a different model of discounting, so we use a different model of altruism. Right, so here is like one simple result, but I think it's a bit surprising. So one very strong fairness concept is equitable. So an allocation is equitable if everyone gets the same utility. So it's probably the strongest fairness notion you can demand.
Not linear?
Sorry, utility period, not marginal utility.
So utilities are not non-linear, they are again concave.
No, here they are linear.
So what does it mean? It means that I get the same amount of money for it?
No, you get
No, it depends on your neighbors, on your discount factors.
Sorry.
Yes, so the marginal benefits are 1 by definition, so it's not hard to get equality of marginal benefits, but it turns out to be hard to get the equality of utility period. Yeah, because
The marginal utility is one only from your next extra dollar,
yeah,
not
exactly.
from your neighbors. Extra
Yeah,
dollar.
exactly. You're right.
A little bit more than one.
But margin utility. If you get the money is 1, so that's what. But the utility function is like this. Right. So an allocation is equitable if everyone gets the same utility. Again, let's assume linear world. Well, it turns out we can get it only for networks where the maximum degrees is 1. Okay, let me actually clarify. Let me actually clarify the results. So if the maximum degree is 1, we can have an equitable allocation for any discount factors. So, like for any discount factors you choose, we can find an allocation which will make the utilities equal. For any other networks, there exist discount factors such that no allocation is equitable. So, for example, for this network, and even for this network or this network, we can find such discount factors that no matter how we divide the money, the society will be unequal in terms of the utility people get.
But the definition doesn't say for any discount factor. What does it say?
Yes, nowhere, like we should have written it more precisely.
Okay.
Yeah, but like here's the intuition. Let me. Can I erase this?
Sure.
Okay, I lower than 1. What is the meaning of degree of I less than 1?
Weakly less than 1. Well, okay, if we have a network like this,
On a chain?
You have
no,
Chain or
on the
one neighbor at most.
singletons or pairs. You have a network where every component is a singleton or a pair, then, like no matter the discount factors, we can allocate money in a way such that all utilities are equal. So that's possible.
But if you have a circle, why not?
What?
If you have a circle.
Circle.
Circle is not degree 1, circle is degree 2, right?
2, why it's not work? Why it doesn't
Okay.
work?
Why will not work? Okay, let me show you on a simpler picture. Okay, suppose we have
3.
we have at least 3 like this. Okay, suppose that this delta is
Well,
very
fair.
large.
For every
Okay, if you use one circle, that's fine. Okay, suppose that this delta 1 is very close to 1. Okay, this is delta 2, very close to 0. Delta 3, very close to 0.
Okay, you want it for every day. Oh,
No,
this
no.
is the problem.
Okay, no, what I want is that there exists delta
That
such that
violates it.
there exists delta such that any allocation violates it. And so for the circle, for example, it's too wide because, I don't know, let's say, for example, Kemal has 2 friends, okay, and also suppose he's very altruistic. So for example, this is Kemal, he's like very, very altruistic. And everyone else of us forms a circle, and everyone else of us is very selfish. So we only care about our own allocation. Well, it turns out, just by direct computation, that's, no matter how everyone else gets, Kemal is happier than anyone else. So even if we assign like 0 to him, if his delta is very large, everyone else's delta is very small, he is going to be happier through altruism. Like basically because if his delta is 1, his payoff will be almost close to 1. Here someone must have lower than 1 because he's very selfish. Something like this. Yeah, are there any questions on this? Right, then if I have maybe 15 minutes, I can show you like some alternative models of altruism. So here, like for now, as you may have noticed, I keep saying like for every like discount factors, for all discount factors, and I'm allowed to play with discount factors the way I want, so I can make, I don't know, UI very, for example, very altruistic, I can make myself very selfish, and so on. Now the question is, what if we assume everyone has the same delta? That is, everyone discounts other people's payoffs the same way. Like, what's going to happen? In this case, some networks which were previously not uniformly efficient become so. And so by uniformly efficient, I mean that every interior allocation is correctly efficient. So one example is with uniform networks. So, like for some reason, we did not see an equivalent definition in graph theory, or maybe we don't understand. But we define a uniform network as a network where everyone has the same number of degree k neighbors. So everyone has the same number of friends, same number of friends, and so on.
That's a regular network, isn't it?
I think regular, everyone has the same number of friends, period.
Right. Well,
But I think, there is a counterexample, that there is a
no, but
regular
what is your definition?
uniform, everyone has the same number of friends, everyone has the same number of friends, and so on.
Sorry. Okay.
Yeah, there is a counterexample that there is a regular network which is not uniform in this sense. So people have different number of friends, even though they have the same number of friends. If you have like network which has full symmetry like this, then if there is the same delta, then every interior allocation is already efficient for any value of this delta. So like here's an example, it's a network like completely symmetric, and like by symmetry it's easy to show that every interior allocation is always going to be very efficient. Now, notice that it has a claw as a reduced subgraph, so the red one. So if we were to assume that deltas could be different,
Sorry, I missed that completely. I thought that an induced subgraph, you take a subset of vertices, that's what I thought.
yes,
And you have to include all the edges from these vertices.
yes,
You do.
yes, but
Sorry,
you cannot draw new edges.
No, that I understand, of course.
Yeah,
You do include all of them. Okay.
Yeah, here is like 6, 1, 2, 4 claw. So if we were to introduce general deltas, then this would not be uniformly efficient in the sense that there would be that all interior allocation would be particularly efficient for some discount factors. But if delta must be the same, then actually all interior allocations are particularly efficient. So like the freedom of choice of deltas actually matters.
So with the uniform with the uniform delta,
Yes.
everything is Pareto efficient?
With the uniform delta for this graph and other uniform networks, every allocation is
So
very
a
efficient. Yes.
claw is fine with the uniform delta?
No.
It's not. But
No, but I
that's
did,
a claw.
I did not. Sorry, claw by itself is not fine, but a network like this, even though it contains a claw, is fine for the same delta.
Because the claw is not uniform.
Yes, claw. Well, it turns out that even in this setting, if we have a claw.
Yeah, I understand. But you say it doesn't work with claw because claw is not under the category of uniform network. Claw itself.
Yeah.
So if you take only claw, it doesn't work.
Okay, here's the thing. I did not tell you anything about non-uniform networks yet.
Okay, but it doesn't include in the theorem at least.
Yes, right. So, like right now, I have not promised you anything about the claw.
Okay.
Right, but like a claw, as you may have noticed, is a tree, and we have results about trees and bipartite graphs. So like first of all, we look at this efficiency for a specific delta. So we ask, okay, for which values of delta interior allocations are going to be rate efficient. And one result, which is especially relevant for trees, is that if we add, well, the result works for everything, but it's just relevant for trees because for trees there is an easier application. So if we add a leaf to a graph, then if it was not uniformly efficient, it does not become uniformly efficient. So if we add a leaf, it's harder to sustain efficiency of interior allocations.
What does adding a leaf mean? I only add one edge?
Yes, you add one vertex and one edge like this.
Okay.
Yes, and if you have a network and it's already uniformly efficient, meaning that you know, at some delta, interior allocations are efficient. If you remove a leaf, then the graph will not become not efficient. So if you remove a leaf, then it's easier to make sure that at some delta, interior allocations are parity efficient. Well, the intuition, I think it's kind of clear because if you add, if you add leaves, then you make some vertices to which you add a leaf more central in the sense, so there's more scope to redistribute. I don't know, maybe if you like add some villages or towns which have connections to Ramat Gan, then maybe it's easy to make some kind of center out of Ramat Gan and create lots of public goods there and benefit the people in the rim. And so if you, I don't know, lose some, some place on the rim, then the benefits of centrality they vanish. Okay. So by the way, this is a contribution of our mathematician co-author. So we have a co-author who's a mathematician from Petersburg State University, and so it's that's his work for the case of homogeneous deltas. Right, and so for trees, we can use this result to actually characterize which trees at which delta are going to allow for the efficiency of interior allocations. So like basically, if the tree has small maximum degree, and if the delta is small enough, then any interior allocation on the tree is going to be efficient. Well, if we have large delta, if we have many leaves, then we increase the opportunity for these characteristic spillovers, so like interior allocations can stop being efficient. Right. For bipartite graphs, like everyone here knows what these are. Right. Okay. I keep when I introduce the bipartite graphs, I keep giving the same. I can keep giving the same examples. I don't suppose we have boys, we have girls, and boys are only connected to girls. Girls are only connected to boys, but boys and girls can be connected. I don't know. Maybe not the smartest example, but I give it all the time. So like we have two groups, and only between group connections are allowed, not within groups. Okay. So it's called like bipartite graphs. So for like bipartite graphs, we have an interesting result that if actually, I think the best way to read it is that if you have one component which is big relative to another, it's not efficient. If they are roughly the same, it's efficient. So for example, if we have, I don't know, many boys and a fixed number of girls, then it stops being efficient. Like, why? Because if there are so many boys, then the girls connected to boys become some kind of more important, like in some sense more central. So reallocating resources to girls is going to benefit everybody, roughly speaking. But if these sets, like these parts, have roughly the same size, then no one is central. So reallocating resources to any person in any other groups doesn't help a lot. Right. So maybe one. yeah, one last result, and after that I will conclude, is that we can assume a functional form that people often ask about, because we often get the question, like, why do you care about your indirect neighbors? I don't know, for example, if Yoav is my friend, but maybe Ziv is not my friend, but he's Yoav's friend, like for the sake of example, then why do I care about Ziv? Maybe I care about my friend, but not about my friend's friend. Well, we consider such assessing for linear payoffs, and we find that here the answers to questions we pose are relatively simple. So here, like an allocation is going to be Pareto efficient for all these count factors if and only if whenever you give money to two people, they're not connected by degree 2. So for example, if, for the sake of example, Ziv is a friend of Yoav, I'm a friend of Yoav, but for the sake of example, I'm not a friend of Ziv, then both Ziv and I cannot get a positive amount of money. And why is that? Because if suddenly all of us, if suddenly Ziv and I become very altruistic, then when we send money to Yoav, it's going to benefit both of us. If everyone else is selfish and properly compensate them, this is going to benefit them too. So a corollary is that if you want to give dollars to everybody, then it's going to be Pareto efficient in this setting only if and only if the graph is complete. So, if the graph is complete, then this problem never allows, never appears. We give money to people, and there is no spillover, like we just discussed with Ziv and Yoav. But whenever the graph is not complete, then such spillover. Then if we give dollars to everyone, then such spillover appears. Okay, so the conclusion is that for such graphs, it's very easy to factorize which allocations are efficient, and which networks allow for efficiency of all these count factors. All right, so thanks for hearing with me so much. That's the end of it. So I think our results have the application that if you are the designer who is in charge of giving out money for some poverty or disaster relief, or maybe you're just giving money for maintenance to some communities, and these communities are tied by an urban network, then if there are altruistic spillovers, like if people care about not just themselves, but what their even indirect friends get, then you cannot, for many realistic networks, this one, you cannot get something which is always going to be both quite efficient and fair. So I think one lesson is that you need to invest in this knowledge if you think these spillovers really matter. So another thing is maybe if you can somehow design a network, for example, if you're the city planner, you can plan how the city will look like, then if your city is an inclusive network, then it's kind of easier to achieve the allocation which are good in terms of fairness and efficiency. So yeah, thank you. Thanks for listening. If you have any questions or comments, I'll be happy to take them.